Yes, so welcome back. Now let us start. We just studied what is a positive definite matrix. Now I want to bring out very that the positive definite matrix is not just a mathematical construct, but it has a very many applications. So we will need to check positive definite matrices later on in many applications. And so first we should get an idea of where positive definite matrices are useful, at least some application, some idea we should get of its application, and then we can later on move towards computationally efficient way of checking positive definite. For example, if the matrix is large and sparse square matrix and we want to check whether it is positive definite or not, then what is a computationally efficient way of checking it? That we will come a bit later on. First, let me just start with an application. So, application most I have come across positive. I have always needed to check positive definiteness in the context of doing optimization problems, both sparse and non-sparse. And so, I'm going to in this video. I'm basically trying to introduce you to this application. So, I will just consider unconstrained problem and then give you a overview over the constraint problem. So let's begin. Consider the problem of minimizing a smooth multivariate function. By smoothness, generally what is implied is that the function can be differentiated any number of times. But actually this application only requires the function to be differentiable twice and and that. So what it means is, suppose it's a univariate function, then df by dx exists everywhere, because I am considering unconstrained optimization. So for a univariate function, it will be over all the real line everywhere, and also d square by dx square exists everywhere, and this, see, if you differentiate, you get again a function. If you can differentiate it second time, you again get a function. And what we are saying is that this second derivative is also continuous. So actually, my definition, my requirement of smoothness for today's discussion is only this much. This is called differentiability in the context of C square. This such a differentiability is usually called as being in the C square. That means twice continuously differentiable. The two at the top of the C square indicates that, and the second derivative is also continuous. That is what is indicated by this. And of course, calculus. Whenever we talk of calculus, continuity has to be there. That I think all of you understand the importance of uh, continuity here. Still, just to recap, this is a continuous function everywhere. Is it not mod of x? This is a smoother continuous function. Is it not like x square plus c? And this is a this has discontinuity at x equal to 0. Now if I differentiate this function, twice, I will get I'll get f double dash to be equal to just 2. So it's continuous everywhere. If I differentiate this function, I get 0 everywhere, but discontinuity at x equal to 0. So this function is not in C square. This function is in C square. And the same concept we have to take to the multivariate functions. So in the multivariate function, when we say it is differentiable, We mean to say that this gradient vector, exists, that is one thing, everywhere. And if you look at the second derivatives, you already have come across this. I'm sorry, you may not have come across, but this matrix of second derivative is called, it's a n cross n matrix. The function is from xn to r. This matrix of second derivative is called as the Hessian matrix, and usually we will be involved with function of this type, which is like del square xi xj evaluated at some x star times xi xj, j equal to 1 to n, I equal to 1 to n. And so this is a function, this again is a function, and we want this function to be continuous. So we want each of these, I'm just using word for sake of clarity, as subfunctions, but they are functions by itself, should be continuous. For example, let us say that I have, let us say that I have a function in 2 dimension, e to the power x1 plus e to the power plus, uh, let's say, into 1 by, or into, say, x2. So if you take its, if you take its gradient vector, it is e to the power x1 times x2 and e to the power x1. Now if you write its Hessian matrix, then this is del f with respect to del x1, this is del f with respect to del x2. So you take once the derivative with x1 itself, so that you will populate this term, then you take its derivative with x2, so you will populate this term, then you take, I'll just write it as x1 x2, take the second function and take its derivative with x1. It should be same as, I'm sorry, because del square f with del x1 x2 is same as del square f with respect to del x2 x1, and then you take a partial derivative with x2 itself, and you will get this as x2 square. So you will get a 2 cross 2 matrix. So now if you do this here, you take this function and takes its partial derivative with itself, e to the power x1 times x2, take this function, takes its partial derivative with x2, so you get e to the power x1, and you take this function, take its partial derivative with x1, so you will again get e to the power x1, and take this function and takes its partial derivative with x2, so you will get a zero term here. Now you can see here that all these four sub-functions, as I have used them, actually they are functions. Again, I am emphasizing that just for my English clarity to you, that I am using that phrase. You can see that all of them are continuous function. So this function is this particular f, is in C square. But now suppose instead I had defined x to be equal to e to the power x1 by x2, then this function is incidentally does not meet any of the above properties, because And if I say that e to the power 0 at the, or rather e to the power x1 comma 0 is equal to 10, you can see that this function has discontinuity at whenever at x2 becomes 0. There are many discontinuities in this function. So the point is, what I am trying to sort of say is, uh, saying that a function is twice continuously differentiable um, is asking quite a lot from that function, but many functions do meet that requirement. And so, we, our first thing in the theory of unconstrained optimization, the positive definite matrices start arriving there itself. The necessary conditions for x star to be a local minimum of this multivariate problem, minimize f a function from Rn to R, f twice continuously differentiable, is that the gradient vector f at x star should be 0, and the Hessian matrix Hx of star, which is the matrix of second derivatives of xi xj evaluated at x star, should be at least positive semi definite. Is positive semi definite. So I'll run it through the proof itself for you. It's straightforward, and that way it is not a black box learning, but rather knowing every nitty gritties of it. So you just look at the Taylor series expansion around all possible directions P. So P is a direction vector in Rn. Alpha is a small step that you take in the direction of P. And by Taylor series, you look at its behavior in the vicinity of x star. What is the function? And what we want to make sure is that when we say necessary conditions, what we want to make sure is that the function should not decrease in the vicinity. That is minimum expectation from our function, that there should be a small enough vicinity in which the function should not reduce. If we can say that in that everywhere around that x star the function increases, then we will call it as a strict local minimum. And otherwise, the necessary conditions are for the local minimum. And there can be functions can have local and global minimum. So like local minimum, local minimum, local minimum, global minimum. So functions can have local and global minimums, but calculus can only, unless the function has some nice features, calculus can only tell you about local minimum, because derivatives, second derivatives, they only evaluate the behavior of the function in the vicinity of wherever you are, in a small enough vicinity of wherever you are. And the primary tool is Taylor series expansion. So if you do Taylor series expansion of this, it is going to be equal to evaluated at x star, the gradient vector being evaluated at x star times of p, plus half of alpha square. Alpha is a scalar here. Alpha is a scalar here. P transpose Hessian matrix, which is evaluated at some alpha theta p and times of p, where theta is a number between 0 and 1. So that means this, for this thing to to be treated as equality, not as an approximation, but to treat this as an equality, the Hessian has to be evaluated somewhere, you know that Hessian, if it is evaluated somewhere between x square and x square plus alpha p, the alpha p being the step that we are taking. So if you evaluate x square somewhere here in between this and this, there is one point somewhere here which makes this to be exactly equal to this. The problem is, the real problem of because of which so much of maths has to be developed is, we know only that there is some theta between 0 and 1 such that this becomes exact, but we don't know really what that value of theta we have to take. For example, if you take theta equal to 0 and instead just replace it with half of alpha square p transpose h of x star times of p, then it is called as a quadratic uh, quadratic approximation. It is nothing more than a quadratic approximation. To make it exact, the theta, it becomes exact provided at some point which is between x star and x star plus alpha p, but we cannot figure that out. Okay, now the necessary conditions for the minimum is that condition for x star. If x star, the way it is said is, if x star is a local minimum, then it must satisfy these two properties. What are these two properties? The properties are the gradient should be 0. This is called as stationary point, and this matrix of second derivative should be at least positive semi-definite. This is known as usually non-negative curvature, because the second derivative has the curvature information about the problem. So if, let's say, let's just quickly run through the proof of it, and no need to quickly run through it. I mean, it automatically will become quick. Let's say that if, let's assume to the contrary, that gradient of x star is, it's already given to you that x star is a, if x star is a local minimum, so given that x star is a local minimum, and assume that this is gradient is not equal to 0, then what I would suggest to you is that you walk against the gradient. So this is usually called as the steepest descent direction. Take p to be equal to minus of the gradient of this, and now if you substitute it here, you will see that your function is fx star minus alpha times gradient of this times, I'm sorry, this is x star is inside transpose x star plus half of, I'll just write this as same way, p of alpha square h of x star plus alpha theta p times of p. So this term here is essentially nothing but minus of alpha, the square of the norm of second norm of this, plus alpha square by 2 p transpose h x star alpha theta p times of p. Now if alpha is very small, okay, then alpha square term, this attenuation term here, alpha square by 2, will make this whole term much smaller than this and this. Why will it make? For example, if it is 10 to the power 3, then this is 10 to the power minus 6, and so on and so forth. So I will not dive too deep into it. I will leave it for you to work on this intuition yourself and formalize this logic. But if alpha is, there is basically what I'm saying is that so long as alpha is kept below a threshold, the second term will dominate the third term, and so the sign of the summation of second plus third term will be decided by second term. Now I have assumed that gradient is not zero, so this term is obviously positive. It's not zero. And if alpha is kept sufficiently small, then because this comes with a minus sign, alpha usually when I say I take a step in optimization, usually it implies that I take a positive step. Alpha is automatically assumed to be greater than zero. So this whole term is positive. So this whole thing is actually negative, and its sign, provided that alpha is kept below a threshold, dominates or determines the summation of this whole second plus third term. So therefore, for small enough alpha, this whole term will become negative, even if I don't know what the theta is. And so I can guarantee that I will reduce function a bit from fx star in the vicinity, which means that x star is not a local minimum. Because if something is a local minimum, then at least in a small enough vicinity, there has to be some small enough vicinity in which the function cannot be reduced. So therefore, I come to the conclusion that then so the fx star can be reduced, or rather fx can be reduced at x star in a small enough neighborhood, which is a contradiction to what, given that x star is a local minimum. Therefore we say that the gradient has to be equal to 0 at the minimum, and this requirement is also said as saying that x star is a stationary point. Now what happens once this thing happens? This expansion now at x star has only the first function. The linear term has vanished because the gradient has become 0. So directly the third term comes into picture, and we write this as so now the behavior of the function at x star being a stationary point, is completely determined by this third term. Now this third term, I should write it more explicitly. I will write it as alpha square by 2. I'll write it as psi of something. We'll see that of sigma I equal to 1 to n, j equal to 1 to n, del square f xi xj pi pj. And p directions I have already fixed. Now whatever choice I am doing. So if you look at this is actually again a function in x1 x2 to xn, and I have already said that my function is twice continuously differentiable. So because I have said that my function is twice continuously differentiable, so this is actually twice continuously differentiable. We have seen one example somewhere here of what we mean by twice continuously differentiable function. And so now assume again to the contrary that this thing here at x star for some pi pj is strictly less than 0. So for some pi pj, some pi pj, this, so I can write this as, yeah, of this is some is strictly less than 0. Now I will use the logic of continuity, and I'll emphasize that this is being done at x star, so this is also, so being done at this have is being done at x star. I'm sorry. So so um, let's say that this term is strictly less than 0. Then continuity says that in a small enough neighborhood, in a small enough neighborhood, this will have to remain evaluated at x star. This will have to be, this will have to remain strictly less than 0, which means that P transpose Hx star alpha theta P will also be strictly less than 0. Remember, theta is being calculated between 0 and 1. So this essentially are, these are essentially the values of the function psi in the small enough neighborhood as we keep changing theta. So by keeping, provided that theta is this and below some threshold, we will be able to make sure that this is negative, which again means that this function will decrease, which is contradiction to the fact that f of x at x star we have a local minimum. So for therefore, what went wrong? What did we assume incorrect? What did we assume to be, our assumption is incorrect, right? That's why we are getting a contradiction. So what did we assume? We assumed that for some p, this term can be less than 0. Sorry, for some p, not this term, this we don't know. For some p, we assumed that p transpose hx of x star times of p can be less than 0, which is a incorrect assumption. So then what is correct, as a correct thing to summarization is, this has to be greater than or equal to 0. But if this has to be greater than or equal to 0, it amounts to saying that h star is positive semi definite. Now, automatically, this does not guarantee a minimum. When you say X star is this is a necessary condition, that then it means that if X star is a minimum, this must happen. So you can use this as a filter or a screening tool to to eliminate those points which for sure are not local minimum. Which is to say that if you check condition 1 and 2, you cannot infer directly from there that your x star is indeed a local minimum. I'll explain this point. Let's take a single dimension function x cube. Okay, now this function, if you sketch, it looks like this. So it does not have a, at x equal to 0, the gradient is 0, and the second gradient is also 0. So 3x square and then 6x evaluated at x equal to 0 is indeed 0. So this meets the requirement of positive semi-definiteness, but it is not actually a it is not actually a minimizer. You can reduce the function reduces here all the way down, and it increases here all the way up. So therefore I said, but now look at f of x equal to x to the power 4. If you look at x to the power 4, its curvature is going to look something very steep like this, similar to x square amplified. Now, in this case also, f of x dash is 0 and at evaluated at x equal to 0, and f double dash is also 0. But here x equal to 0 is in fact a, a global minimum, not only local, it is actually a global minimum. So our necessary condition says that if you are at a minimum, this must happen. This is fine. So, and it is happening. But you cannot apply it necessarily the converse way, which is that if I find something which meets this there, then I can say that x star is a minimum. This would happen if you are giving a if and only if condition or necessary and sufficient condition, which usually in optimization is difficult to give. So usually we give a separate set of necessary conditions and a separate set of sufficient we give separate set of necessary conditions and separate set of sufficiency condition. So a separate set of sufficiency condition for our unconstrained optimization problem is that first is necessary conditions have to be a subpart of it. So this will be 0, and the Hessian matrix is positive definite. Sometimes I just write it as saying that this is strictly greater than 0. But this is just a notational thing that I'm doing. What I mean by this is x transpose hx star of x is greater than 0 for all x not equal to 0. This being a vector in Rn. This being a vector in Rn. So that it is positive semi-definite, which was a part of the necessary condition, that is already embedded here when I say that H star is positive definite. In fact, Hessian is a symmetric matrix, so therefore this is sometimes also called as Hx star is SPD, the symmetric positive definite matrix. And why would if H why is this sufficient? Because if this is positive definite, then I know that P transpose Hx star P is greater than 0 and by continuity the C square property that I used, this continuity says that therefore in small enough vicinity also H square P transpose Hx P will be greater than 0 in a small enough vicinity near x equal to x star, which basically guarantees that this, if I consider theta small enough, theta already I know is between 0 and 1, but I could say, for example, theta between 0 and 0.5 or whatever, that small enough vicinity, this term will always be greater than 0, and therefore the function will always increase in the vicinity. That small enough neighborhood, the function will always increase, which guarantees that x star is a local minimum. Such a local minimum is also called as strict local minimum. So Hessian in an unconstrained, to summarize, in an unconstrained optimization problem, if I have a stationary point and if hx star is positive uh, definite, then symmetric positive definite, then I have guarantee for it being a local minimum and it being positive local minimum and it being a strict local minimum. It not being a strict local minimum is essentially to say that I can have a curvature like this. Suppose this function comes here, stays at this value, I'm sorry, stays here and then increases. A flat surface. Now again the same thing. If it is a flat surface, second derivative does not tell me whether after some time it will become like this or not. So that's why it cannot give me a sufficiency condition. Okay, so now you know why positive definite matrices are critical for if for finding out checking um, the local minimas of unconstrained minimization problems. Why they play such an important role? And if you don't check they are positive, definite or not, how will you say whether you are at minimum or not? So this course will enable you to exactly give you the Kulosky decomposition technique later on to evaluate the positive definiteness of a Hessian in a computationally efficient manner. Now let's look at application number two. Application number two is minimize f of x subject to some set of linear equality constraints. So I call this as problem equality LEP problem. It is called as LEP problem. I'll call it linear equality constraint programming problem. Again, f is a function from Rn to R, and I am taking f to be twice continuously differentiable, and my requirement is and the necessary conditions and sufficiency conditions for optimality are as follows. The necessary condition is that uh, I call this as projected gradient x star. If x star is a local minimum, then the projected gradient should be 0 and the projected Hessian should be positive semi-definite, where Z is a null space basis of A. So I will not give you full proof, but I'll explain to you. This shows that one way you know how to calculate null space basis used to use QR decomposition. Is it not? We have seen that. We have also seen actually we can calculate null space basis from singular value decomposition, but QR would be a much better way. I would suggest to you if you have to calculate in a numerically stable manner a null space basis. So basically, I'll give you only outline. No, I'm not going to prove this, but I'm only going to give you outline of the proof, which is that if x star is the local minimum and z is a null space basis, that is to say az is equal to 0, then all points, this is the characterization of set of all feasible points for this optimization problem. What are the feasible points? The points which meet ax star ax is equal to b. This is because, why is it so? Because when I look at ax, it is ax star which is b plus azp, but this is b and z being null space basis is 0, so it is 0. So all these points are essentially the feasible points. And if I have two feasible points, let's say x bar and x cap, and I look at the difference among the two, then ax bar minus ax cap is 0, which means that x bar minus x this thing has to come from the null space. It has to be, this vector has to belong to the null space, so it can be represented as a linear combination of z times some alpha vector, and therefore basically if you take this to be same as x star, then you see that this point, any other feasible point, can be written as follows. Maybe I will use here also alpha because p sometimes we have used it as an n-dimensional vector. So and this null space basis means its dimensionality, number of columns is equal to the dimensionality of the null space basis. So therefore set of all feasible points can be characterized by this, and once we know this, then we can convert our original mean constrained linearly constrained optimization problem to a unconstrained, take any point in which our case it is x star plus alpha times alpha is actually used as scalar, so I should not have used alpha here. Maybe I should have used something like q, for example. And so alpha times zq, and where q is a dimension in the vector. Suppose rank of A is m, then in that case Z will have a dimensionality, null space will have a dimensionality of n minus m. So therefore, the number of linearly independent columns in Z will be n minus m. So Z will be therefore a n into n minus m matrix, and so the Q vector will have to be n minus m cross of m. So now this, in a reduced dimensional problem, this is the unconstrained minimization problem. So whatever we have learned for the unconstrained minimization, that theory can be applied here, which is that the gradient of this function should be zero. So you can call this function as g of q, and its gradient at q equal to 0 should be 0, and its second derivative Hessian matrix should be positive semi-definite, which translates, if you expand it further, translates to this requirement that the projected gradient should be 0 and the projected Hessian should be positive semi-definite. And if further this projected Hessian is positive definite, then you can again show that the second derivative term will be always greater than 0 for q not equal to 0, which is to say that the function will increase anywhere in the vicinity of x star, provided that your point is not only in the vicinity of x star but also feasible. So the feasible vicinity of x star, in that the small enough neighborhood, the function will also increase, which is to say that I am at a strict local minimum. So again, we saw some interesting application of uh, uh, Hessian requirement to check positive definiteness of Hessian. Now, third application, again I am choosing because I do some studies in convex, not convex, I do some studies in optimization, so I have to frequently use this aspect, so that's why I'm emphasizing this aspect to you. The third problem is, which I'm going to look at, is minimizing convex functions. In fact, there are books devoted to convex programming, as it is called, and a convex function. So we first of all need to define a convex function. So let's say f is a function from set S to R, where S is some open subset of Rn. It could be Rn itself. There is no problem. It could be even Rn, but S is in general open subset of Rn. If I take 2 points x and y in S, and if f is convex, then it means that if I look at this is called as a convex combination of x and y. That is, if say this is a point x, this is a point y, then convex combination is set of all points between this and this. So this is f of x, and or if in a two-dimensional space, x1 vector, x2 vector, this is one point, this is another point, let's call this as x, let's call this as y, then the set of all points, including the corner points, the set of all points between x and y are called as the convex combination of x and y, and they can be represented as this, where alpha is a scalar between 0 and 1. If you expand this, this is saying that this is y plus alpha times of x minus y. So it means you start at y, and move in the direction of x minus y. So you move in this direction, and alpha is between 0 to 1. So 0 is here, you are at point y, and you keep increasing alpha. When you reach alpha equal to 1, y plus x minus y, which is x, so you reach this point x. Hence this thing that alpha should be between 0 and 1. So this is known as all convex combinations. And the requirement of a convex function is that fx, if the function f is convex, then this should be less than or equal to alpha x plus 1 minus alpha times of f of y. The convex functions have huge many applications. I will not get into it. You can refer to a book by Stephen Boyd, for example, which deals completely with very many interesting applications of convex programming. But uh, roughly speaking, what this means, not roughly speaking, what this means is, say for example, I have a function like this, and this is incidentally x square function. I take this, let's say, as x, this as y. If I join these 2 points, now if I take any point in between here, for example, this is a convex combination of x and y, and the function value which is evaluated here is less than or equal to the linearly interpolated value f of x and f of y. If I do a linear interpolation by fitting a line, I will evaluate this, which is the RHS, and actual function value is less than or equal to this. If this strict inequality holds everywhere, then the function will be called as strictly convex. And one interesting property is that of a strict convex function, of a strict convex function is that it is symmetric positive, it's Hessian, it's Hessian, it's Hessian is symmetric positive definite everywhere. So that's such functions have, incidentally, so very easy to check that fx equal to x square, this is a property, this is if and only if property. If it is SPD everywhere, then you can also say that the function is convex. So for example, f of x square is convex function because its second derivative 2 is SPD. If you take x1 square plus x2 square, then x1 square plus x2 square, its positive is also strictly convex because its Hessian matrix is twice the identity matrix. So there are many applications of, there are many examples of convex functions. And again, positive definiteness of the matrices plays a very important role there. The last thing that I'm just going to mention and move on, or rather close this video, is the very generic yet, I mean, differentiable, smooth, that kind of optimization problem. F is a function from Rn to R, and I have a set of variables which I have a set of equality constraints, g1x to be equal to 0, g2x to be equal to 0, and so on up to gr of x to be equal to 0, and a set of inequality constraints, and assume that all these functions are twice differentiable and continuous, that is, all of them comes from c square. Then in when I write what is known as the, I'm not writing it now, but if I write what is known as the Karush-Kuhan-Tucker optimality conditions, again the positive definiteness of the projected Hessian comes into play in checking, in verifying, in ascertaining that I am at the local minimum. And it also is a cue to how to go about finding a local minimum of such. very generic optimization problems. So we now have come to a very important conclusion that study of positive definite matrices is very important and it should be taken up. Thank you.